All right, we're going to talk about applied optimization. So just remember what that means is you're going to either maximize or minimize an equation. And so when we're looking at that, maximizing or minimizing, we're really looking at, in calculus, that derivative and that critical point, right? We've talked about taking the first derivative, finding the critical points, and plugging those in. So applied optimization, these are kind of the steps here. So the first thing is read the problem. Read the problem as many times as it takes for you to fully understand it. A lot of times when we read story problems, the first thing is we look at a story problem and go, oh, it's a story problem. And so the first time we read it, we just kind of like zip through it because we're like, oh, it's a story problem. Sometimes you have to reread that multiple times. The second thing, draw a picture. Okay, it is really important if you draw a picture. Now you can kind of start labeling things, understanding what you're trying to get. This drawing a picture will probably help you in understanding the problem. Introduce the variables. What does the variable represent? Those kind of things. Sometimes we kind of, on this step here, we tend to just kind of assume that people understand it, and as we kind of progress, a lot of times if you're doing this for a formal paper, you want to actually physically write out X is the length of the side, R is the radius of the base circle, so on and so forth. Okay. Write an equation for the unknown quantities. Sometimes these kind of go hand in hand as you're working it. So we want to write the unknown quantities. So we want to get everything into algebraic terms, variable terms, that kind of stuff. Test the critical points and endpoints in the domain of the unknown. Okay, so we're going to test that. This is calculus. We're going to find that critical point. So our example 1. So it's talking about we're creating an open-ended box by taking a 12 by 12 square sheet of tin and cutting small congruent squares out of the corners. Okay. And bending the sides up. So we're going to take this, bend it up. Here's my diagram. What's going to happen is I'm going to cut out a square at each corner, and then I'm going to take that flap and bend it up to create a box. Okay? So X, so I'm going to go X is the length of the cut. Okay? So it's going to be how long is that cut. Now I've already kind of drawn up some of this. So how large should the squares be to maximize the volume? So my problem is I'm trying to maximize that volume of that box. Okay? So I notice here that when I cut this square out, the length here is going to be 12 minus x and x, which is 2x. So 12 minus 2x, and that's going to be all my sides. Okay, so I need to understand what the volume of a box is. So the volume is length times width times height. Okay, my length is going to be 12 minus 2x here. My width is going to be 12 minus 2x. And my height is going to be this piece bent up, or x. Okay, now, so this is my volume piece here. If I multiply this out, I get a volume is equal to 4x cubed minus 48x squared plus 144x. This is just there to maybe help you a little bit and see that pieces. My endpoints of my thing. So my x could be, my smallest it could be is 0, which would be just a flat piece of tin there, and I'd have no. It could be 6, but the problem is if I cut this at 6, I'm right here, right? So I actually have no width. Okay, so those are my endpoints. Now, I'm going to take my derivative. So the derivative of 4x cubed is going to be 12x squared minus 96x plus 44. So there's my derivative, right? I'm just using primarily the power rule. I'm going to factor out a 12 to get this to be in a little bit easier format. So when I factor out a 12, I get 12 times the quantity x squared minus 8x plus 12. I'm going to factor this into x minus 6, x minus 2. Well, 6 is already my endpoint, so it's not really it is a critical value, but it's also my endpoint. So if I were to plug in 6 and 0 into this formula here, I would get 0 times 6, which is 0, so my volume would be 0. If I plug in 6 here, if I plug in 0, I get 12 times 0, which is 0 again, so my volume is 0. So my critical value has to be at 2. Okay, so this has to be my maximization. So I'm going to plug in 2, so I get 12 minus 2 times 2, quantity squared times 2, so 12 minus 4 is 8. 8 squared is 64. 64 times 2 is 128 inches cubed. Okay, so that's my maximum volume. And it's going to occur when I'm going to take a 2-inch cutout of each corner. Okay, so that's our first one. All right. Now, our second one is talking about, you've been asked to design a 1-liter can shaped like a right circular cylinder. What dimensions will use the least amount of material? Okay, so I drew up my can here. So I have a radius, I have a height of my can. So I want to make sure that I have that idea there. Now the next thing I'm going to do is I'm going to look at my volume and understand what it's talking about. Okay, so I have to understand what 1 liter is equal to. Well, 1 liter is equal to actually 1,000 centimeters cubed. Okay, so that's important to understand that piece there. And so now my volume is pi r squared h, but that's going to equal 1,000. And if I look at my surface area formula here, we're going to kind of jump down and then jump back up to where this h equals. I have 2 pi r squared plus 2 pi r h. So both of these have the r variable, or the radius of my base, circular base there, and it has the h. So I actually want to solve this for h up here. Okay, so I want to actually get rid of that h. So I'm going to solve up here. I'm going to solve for h, which is going to be 1,000 over pi r squared. I'm going to take this, substitute it in for h, just to simplify my expression. So when I do that, the pi's cancel out, one of the r's cancel out, and I get a surface area of 2 pi r squared plus 2,000 over r. Okay, I'm now going to take the derivative of that. Well, the derivative of that, I'm taking it with regards to r. So what I should do is I could write this as dA dr. Okay, that gives me an idea. I'm taking the derivative of my area with regards to my radius. Okay, so if I can find my radius, I can always find my height, because my height is based off my radius. All right. Now what I'm going to do is I am going to set this equal to 0 and solve. So I'm going to set this equal to 0. I understand most of you guys don't like working with fractions, so let's get that fraction out of there. So what we're going to do is we're going to multiply both sides by r squared. So this gives me 4 pi r cubed minus 2,000 equals 0 still. Well, that's nice. Now I only have 1 r, so I'm going to add my 2,000 over. I get 4 pi r cubed equals 2,000. Now I'm going to divide by 4 pi. Okay, I get r cubed equals 2,000 over 4 pi. And now to get rid of my cube, I'm going to cube root it. Okay, so now I get r approximately, I'm going to go ahead and use a calculator to find that. R is approximately equal to 5.42. Okay, and now I can find my height. Okay, so I'm going to find my height by coming back over here and plugging it in. So I have 1,000 over pi times 5.42 squared, and I get a height of approximately 10.84 centimeters. Okay, so now I have a radius of 5.42 centimeters. roughly about 2 inches. So it's about 4 inches across, pretty big can, and 10 centimeters high. Okay, so when we're looking at optimization, you're going to want to find that derivative, set it equal to 0, and then solve for the variable that you've taken the derivative with regards to. That's going to give you those critical points. So 2,000 divided by 4, that gives you 500 over pi. 500 pi cube root of that, going to roughly give you close to about 5.42. Okay, solve for the other variable if you have it. All right, so that's optimization. So remember, we're really looking at the derivative, finding those critical points, and playing it back in. This is kind of how it works in the real world, how we're using calculus to solve real world problems.